Welcome to the deep dive. Today we're embarking on a mission, really, to demystify something absolutely fundamental,
Yeah.
something that powers our entire world, electricity. And for this particular deep dive, we're really focusing on breaking down electric current, trying to make it make sense at a beginner's level,
Yeah, absolutely.
helping anyone, even if you've never touched a wire, feel well informed. Our goal, to understand what current truly is and, well, how it moves. Okay, let's unpack this.
And that's such a crucial starting point, really. If you can grasp the essence of electric current,
Mm.
well, you'll find that so much of electricity just clicks into place almost immediately.
Right.
We've gathered some fantastic material that makes these sometimes complex ideas surprisingly clear, and it reveals some incredible facts hidden in plain sight.
Okay, so to kick things off,
Mm.
let's start with a picture that really helps. Imagine water flowing through a pipe.
The classic analogy.
Yeah, that simple image is actually a powerful way to visualize electric current, isn't it?
It truly is. It's fascinating how well that analogy holds up. Because just as we measure water flowing in, say, liters per second,
Okay.
we measure the amount of electric current using amperes, or, amps for short.
Watts, right. Got it.
And when we talk about 1 ampere, that's essentially 1 coulomb of charge moving past a point in 1 second. Now, coulomb might sound a bit technical,
A little bit, yeah.
but you could just think of it as a specific, huge group of electrons,
Yeah.
like saying a dozen eggs,
Ah, okay. Just a quantity.
Exactly. So in simple terms, current is precisely how much electric charge is moving. The big takeaway. A higher ampere number just means you have, well, more electricity on the move.
Flowing.
More current flowing, exactly.
That makes a lot of sense. So we've got this flow, like water in a pipe, but what's actually making that water or, the electricity flow? Does it just happen, or there's something pushing it along?
That's a great question. No, it doesn't just happen. You need a push. Just like a pump creates pressure to make water flow.
Right, the pressure.
In electricity, that push is called a potential difference.
Yeah.
Sometimes people just call it voltage.
Okay, voltage. I've heard that.
Yeah. When that electrical pressure, that voltage, is applied, it causes tiny, negatively charged particles within atoms called electrons to move.
Electrons, okay?
And this very movement of those electrons is the electric current. So when you flip a switch, you're basically applying that push, that voltage,
Getting the electrons moving.
and getting those electrons dancing. That's right.
Okay, but here's where, for me at least, it gets really interesting and maybe a bit counterintuitive.
I think I know where you're going with this.
Most of us probably learn that electricity flows from positive to negative, right? That's sort of the standard diagram.
You're absolutely right. That's the conventional understanding. It's what we use every day in diagrams and calculations. But here's that fascinating paradox we found in the source material.
Yeah.
While we conventionally describe current as flowing from positive plus to negative, the actual physical movement of those electrons we just talked about,
Uh-huh. The ones doing the dancing?
those exact ones, they actually move from negative to positive plus.
What? Really? So they're opposite?
They are exactly opposite. The direction we say current flows and the direction electrons actually move are completely opposite.
Why? That seems confusing.
It's a quirk of history, really. It's simply due to historical conventions. Benjamin Franklin and others made assumptions about flow direction before the electron was even discovered, let alone understood.
Ah, so they guessed, basically.
Kind of. They defined positive and negative and the flow direction associated with them. And once a standard like that is set, especially in science and engineering, well, it's incredibly difficult to change worldwide.
I can imagine.
But the key insight is, for all practical purposes, like designing circuits or fixing things, using the conventional flow from positive to negative works perfectly fine. You just have to remember what the electrons themselves are actually doing underneath.
That's truly mind-bending. Okay, so if these electrons are doing this invisible dance, how fast is this current moving? I mean, are we talking slow, fast?
Oh, this raises a fantastic question. And the answer is, well, it's astonishing.
Lay it on me.
Electric current is known to travel at the speed of light.
The speed of light. Seriously.
Seriously. That's an incredible 300,000 kilometers per second.
Wow.
Fast enough to go around the entire Earth 7.5 times in just 1 second.
Okay, that's almost unfathomable. But hold on. If the current travels at light speed, How can that be? I thought I read somewhere that the electrons themselves don't actually move that fast at all. They sort of drift along quite slowly, don't they?
That's a brilliant observation. You're right, the individual electrons don't race along at light speed. They drift relatively slowly, actually. Seems like a contradiction, doesn't it?
It really does. How can the current be light speed if the electrons aren't?
This is where another analogy really helps clear things up. Imagine a long tube, or maybe like you said, a line of billiard balls, all packed tightly together.
Okay, like a whole row touching.
Exactly. Now, if you hit the first billiard ball, what happens to the last one?
It shoots out almost instantly.
Almost instantly, right. Even though the first ball you hit only moved a tiny bit and all the balls in the middle just nudged the next one.
Yeah, the impact travels right down the line.
Precisely. Electrons in a wire behave similarly. It's not one electron zipping from the switch to the light bulb at light speed. Instead, when you apply the voltage, it creates an electric field that propagates through the wire at light speed. This field makes all the free electrons along the wire start drifting almost simultaneously.
So it's the signal or the effect that's light speed.
Exactly. It's the push, the energy transfer that travels that fast, like that ripple through the billiard balls. So when you flip that switch, the light comes on seemingly instantaneously because that push travels at light speed, getting the electrons moving everywhere in the circuit almost at once. It truly feels like it happens in the blink of an eye.
That billiard ball analogy.
Yeah.
Wow, that instantly clears things up. Much better. Okay, so if this effect is traveling so incredibly fast, what kind of pathways does it prefer? Does electricity just travel through anything? Wood, plastic, air?
Good question. No, not at all. The materials we looked at explain that electricity really likes materials where electrons can move easily. These are called conductors.
Conductors, right.
And the best conductors are typically metals. Think copper, gold, silver, aluminum. They have lots of electrons that aren't tightly bound to their atoms and are free to move.
That's why wires are made of metal, usually copper.
Exactly. Copper is so common because it's a great conductor and it's relatively inexpensive and easy to work with. So when you apply that voltage, that electrical push, to a copper wire, those free electrons are easily set in motion, allowing the current to flow.
Okay, so let's bring this back to something practical. Why is it so important, say, for an electrician that this current flows well? You mentioned the push, but what about the path itself?
Right. It's crucial. Think about it like plumbing again. You want water to flow easily out of your tap when you turn it on, right? You don't want clogged pipes.
Definitely not. Makes total sense.
It's the same idea with electricity. Most electrical problems, when you really boil them down, stem from issues with the current flow. Either it's not flowing well enough.
Like a blockage.
Exactly, like high resistance, a bad connection, a broken wire, or sometimes it's flowing too much.
Oh, like a short circuit.
Precisely, like a short circuit, which can be dangerous. The source material actually used a neat analogy here, comparing electrical pathways to our circulatory system.
Oh, yeah. How so?
Well, it mentioned arteriosclerosis, hardened arteries impeding blood flow. For electricity, it's pathways, the wires, the connections, the components they need to be clear and unobstructed for things to work properly and safely.
So understanding how current flows and what helps or hinders it is key.
Absolutely crucial. For everything from designing efficient electronics to just figuring out why your lamp isn't working, it all comes back to the flow of current.
Wow. Okay. So let's recap. What does this all mean? We've gone from water pipes to billiard balls hitting each other. We tackled that really surprising paradox about the direction of flow.
The electrons going the wrong way.
Yeah. And we clocked the speed of current at the speed of light itself. If you followed along, you've just taken a massive step, really, in understanding this invisible force that powers pretty much everything in our modern world.
Absolutely. And if you've grasped these core concepts, what current is, basically charge in motion, and how it flows, pushed by voltage and traveling as an effect at light speed, then, well, the source material suggests you've already understood maybe half of electricity right there.
That's huge.
It really is. It makes you think, doesn't it? Just consider how many everyday devices all around you rely completely on this incredibly fast, visible flow happening correctly. What new questions does this spark for you now that you have this picture in mind?
That's a great point. So next time you flip a light switch or plug something in, maybe just take a moment. Consider that incredible, almost instantaneous dance of electrons happening inside the wires, the sheer speed at which that energy is delivered right to where you need it. It makes you wonder, what other invisible forces might be constantly working around us, forces that we've maybe yet to truly unpack?